Stripping down science. The Naked Scientists.
Hello, it's Sunday the 15th of January in 2012. Welcome to The Naked Scientist. I'm Chris Smith, and also here this week is Helen Scales. Hello, Helen.
Hello.
Now, this week we're taking the human experience to the next level because we're exploring cybernetics, including a new visual implant that could restore vision to blind people and brain interfaces that can directly decode nerve activity to control robotic arms and other devices.
And in other news, we'll hear from the man who made an H5N1 flu virus with pandemic potential, but he then found himself at the centre of a scientific controversy.
Indeed, the work can't actually be published over fears that terrorists could cook up their own version of the virus he's made. But Ron Fouchier did talk to us about his other concerns.
Many of the mutations that we have introduced with genetic modification are already found in the field. So it's now a matter of chance of a mammal running into a chicken that has a virus with those mutations. And then in that mammal, it can accumulate the extra mutations, and then we would be in trouble.
We'll have the full story later in the show. Meanwhile, if you have any questions or comments for us, tweet at Naked Scientists, right on our Facebook page. That's at facebook.com/The Naked Scientists, or drop us an email. Our address is chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This week, we're exploring the world of cybernetics, cyborgs, and enhanced humans. It's the stuff of science fiction, but it has a solid base in reality. Well, to find out more, we're joined by Kevin Warwick, Professor of Cybernetics at Reading University. Hello, Kevin. Thanks for joining us.
Helen. Good to speak to you. Yep.
Fantastic. Well, let's kick things off with a bit of an introduction to what we're talking about this week. So what is cybernetics? What are we on about here?
Well, it is humans and technology linking together. So it's the whole system. It's looking at how it all works together. So lots of practical examples. But as you've spoken about cyborgs, which is perhaps has been more of a science fiction thing in the past, where the technology and the human are integral. They're not separable, as it were, and the abilities possibly could be much, much more than humans alone.
Perhaps there are things that we might not consider as being sort of cybernetics. I mean, are things like pacemakers and cochlear implants? We're quite familiar with that sort of technology. Does that count?
Well, to some people it would. I mean, it's interesting to me. I'm involved working with Tipu Aziz at the John Radcliffe Hospital, Oxford. They implant the deep brain stimulator. This is a long electrode, actually about 4 or 6 electrodes on the end of a long wire, pushed into the centre of someone's brain, into the subthalamic nucleus, right? It's a very small part of the brain. And an electrical pulse is applied there to overcome the effects of Parkinson's disease. It's also being used now for depression and even in some cases for Tourette's syndrome. But what's interesting now is we can also take signals from the electrodes and monitor what's going on in the brain, hopefully to try and predict when people's tremors are going to start, things like that. But it's also giving a new insight in what the disease is. So you could regard it as a cyborg, whatever. In terms of cybernetics, it's giving us more of an insight to actually what's going on in the person's brain.
And what about the more far-off things we might actually consider science fiction, really mixing machines with people? Where are we at with that kind of thing?
All sorts of possibilities. I mean, one of the things we have done, growing neurons, culturing neurons, and then linking them up to a robot body. I mean, either they're typically rat neurons, because you do all sorts of things with rat neurons, but also human neurons. So we can actually look at how the neurons learn, how they connect together to make the robot move around and avoid objects and things like that. And in that sense, by applying new neurons or stem cells over time, you can try and keep some of the memories, some of the way the robot operates in terms of this biological brain, keep it going, which will give a bit of an insight into things like Alzheimer's in terms of when neurons are dying off, can we add new neurons and so on to keep the brain going. So it could help in the long term, but it's fun at the moment and it's experimental. It's very sort of frontline science.
I have to say, one of the things that fascinates me the most is the idea of extrasensory perceptions, the idea of plugging myself in and being able to see or sense things that currently I can't.
Yeah.
Where are we with those sorts of areas of cybernetics?
Well, I mean, the implant that I have had, which Andy Schwartz, who's on later, he will talk about, maybe I shouldn't spoil it for people, he'll talk more about what the implant can do. But in my case, it was fired into my nervous system and I was able to experience ultrasonic signals. This is like sonar signals, which gives you an indication of distance. So it had ultrasonic sensors on a baseball cap, and literally the output of those were fed in via the implant into my nervous system. So I learnt to recognize the pulses over a period of 6 weeks, but then was able to use it to detect where objects were. So it's only a small way. It's like extending the senses, if you like, or having an ultrasonic sense, but it shows that we can do that. And therefore, in the future, having things like infrared may be stretching to things like X-ray. So it's not having a different visual. It's not seeing something, but literally it is sensing it in a different way. The human brain is very plastic, very adaptive in that respect.
And how did your brain adapt to having this implant taken out? That must have been quite strange to go back to normal.
I have to. I mean, this is a science program, and I have to say one of the key things was we were absolutely exhausted. This was 3 months of research, and at the end of it, I think we were in the lab every day. So I was a lab rat in that sense, and I think exhaustion was the overriding thing. It was only something that we were doing in the lab, so sort of from time to time. It wasn't something that I was using in everyday life. I think if it had have been, if I had this ultrasonic sense as a sort of permanent thing for a couple of months, I would have missed it, yes. But it was something we were really just experimenting with in the lab, so it wasn't such a problem when it got taken out. It was the end of the experiment. We wanted to look at what had happened to the implant and what had happened to the nervous system and things like that. So that was part of the experiment, part of the trial was that as well.
And looking ahead, where are the big challenges that lie ahead of you in terms of all of this research you're doing? Would you say it's the scientific barriers that you have to break through, or is it the ethics, actually? I mean, that must presumably throw up a whole lot of issues tangled up with the idea of, part people, part machines, and where that's taking us.
Yeah, I think it's a little bit of everything. That power is an issue. How do you power implants? Particularly if something's in the body, can we use body power? And there, I think possibilities with wireless transmission of power, that's tremendously exciting at the moment. So this is something Nikola Tesla spoke of. At the moment, if you in your home you've got power provided by wires, the possibilities of wireless power, that's certainly something we're researching. That could, if it can be not just affect implants, but could affect vehicles. We can have powered vehicles, remotely powered vehicles, so it's tremendously exciting. But I think ethically, almost self-imposed ethics are one of those things. You don't want to injure somebody, you don't want to cause problems, but at the same time, ethics to do with human enhancement, which is a possibility, extra memory, new ways of communication, is very difficult to decide what are the ethical aspects, because it could be commercial opportunities, but it could also affect an awful lot of people.
Yes, it's all very exciting to think what might lie ahead and what the options might be. But I think we'll leave it there for now, Kevin. Okay. That was a fantastic intro to the world of cybernetics. That was Kevin Warwick from Reading University.
We're here this week talking about implants and cybernetics and making us part man, part machine. And as we've just heard, these sorts of things can actually change people's lives, or they will do in the future. Taking a present example, the cochlear implant has been around since the 1970s, and that has helped over 200,000 profoundly deaf people to regain some sense of their hearing. Well, now the stage is set for the visual equivalent of the cochlear implant, and a team based at Oxford University are developing an implant that will return sight to people who have lost their natural vision owing to disease processes like the disease retinitis pigmentosa. And we're joined now by Dr. Marcus Groppe, who's from the Nuffield Laboratory of Ophthalmology. Hello, Marcus.
Good evening.
Let's first of all look at what the disease is that you're trying to remedy. So can you just fill us in on what retinitis pigmentosa is?
Retinitis pigmentosa is a genetic disease, so a condition which is passed from generation to generation. And it's kind of a mixed bag of conditions which are all grouped under the same name. The main problem is that patients with this condition will lose their photoreceptors. So in our eye, at the back of the eye, we have a layer of cells which make up the retina, which works a bit like a sensor in a camera or film in a camera. And one layer of the retina are the photoreceptors, and these photoreceptors convert light energy into an electric impulse. And patients with retinitis pigmentosa have genetic defects which don't allow these photoreceptors to work properly over a long time, and with their lifetime they will get more and more degeneration of photoreceptors. Most of these patients are initially affected by losing peripheral vision and night vision, but later on, quite a lot of these patients lose central vision and eventually end up being blind.
And the disease is manifest just within those photoreceptor cells that convert the light waves into electrical signals, but presumably you leave the other structures in the eye, including critically the optic nerve, intact.
Yeah, in most patients, if you wait long enough, there will be some more degeneration in layers of the retina which make up cells which form the optic nerve, and there will be some degeneration. But by the time point patients actually become blind, the ganglion cells which form the optic nerve are still intact in most of these patients.
So if you can get signals back into them, then you can help them to experience at least some semblance of vision again. Is that your starting hypothesis?
And that is exactly the idea behind the retina implant. The retina implant we are using in our clinical trials, which will start very shortly here in Oxford. It is a chip which contains light sensors and an amplifier which converts the light energy into an electric impulse and then can connect to the ganglion cells so that the information of light is sent to the brain via the optic nerve.
So because you've lost the photoreceptors, the bits that see the light, your chip takes the place of those photoreceptors you've lost and then couples itself onto these ganglion cells that make the optic nerve that would transmit that signal into the brain.
That is correct. And the chip sits exactly at the same place where the photoreceptors used to be before the degeneration took place.
Wow, how big is it then?
The actual active part of the chip is 3 by 3 millimeters and contains 1,500 light sensors, so which gives you obviously a quite pixelated picture, but theoretically can give enough information for patients to be able to read big letters again. But the main aim is to give patients who are completely blind some visual sensation back, which helps them in everyday situations. For example, to find a door frame, or to see a plate in front of them on a table, or to find things in the environment which they misplaced, which is very difficult for a blind patient who is only reliant on his feel and touch sensation.
How do you get the chip in the first place?
It is an operation where a pocket of fluid is created via an injection underneath the retina to create some space for the chip to slide in. And then a tunnel is created through the sclera, which is the white leathery bit of the eye. And the chip is then sliding towards the center of our retina, the macula and the fovea, and is placed just underneath these structures because that allows the highest density of ganglion cells to project the best quality of picture to the brain.
And how do you power the chip?
The battery power is the same technology as it is for cochlear implants. So it is a magnetic plate sitting behind the ear, and the chip is then powered by electromagnetic power. So everybody runs around with a small battery pack, which then clicks onto the skin behind the ear via a magnet.
And what data have you got so far that this is going to be a success? The fact that you're going into humans argues that you must have satisfied enormous amounts of regulation and other preliminary data requirements to show that this is likely to work. But how soon do you expect to see results?
At this stage, we are involved in a multi-center trial in Oxford here. So most of the work for this type of chip, and there are a few other types of chips, was done in Tübingen in Germany. And currently, the state is that at the stage 1 trial, 11 patients have been implanted in Germany, and we will be starting to implant, hopefully in a few months, in Oxford, the first patient.
And how many people are you going to do in total, and when will you know whether or not you've got a success on your hands? What's the long-term follow-up here?
The trial is set to follow these patients up for 1 year, and depending on the outcome, we are planning to do 18 patients in altogether 5 centres, but that can be extended to about 32 patients.
Super. Marcus, we'll leave it there just for now. Marcus, just as Kevin is, will be with us for the rest of the programme. So if you would like to ask Marcus Groppe, who you just heard there from the Nuffield Laboratory of Ophthalmology at Oxford University, a question, you can send us an email, chris@thenakedscientists.com, or we have a Facebook page, facebook.com/thenakedscientists, or you can tweet @nakedscientists. First, though, let's take a look at some of the stories that are making scientific headlines around the world this week. And first up, a controversy that's even got governments involved. In September 2011, Dutch researcher Ron Fouchier gave a presentation at an influenza conference in which he showed how he'd been able to make, relatively easily, a form of bird flu, H5N1, that can transmit readily between mammals, which is something that the naturally occurring form of the virus, thankfully, can't yet do. The results describing the structure of what Ron Fouchier himself describes as probably one of the most dangerous viruses that you can make were sent to the journal Science for publication. But the paper has been suppressed on safety grounds, lest the details could aid terrorists in creating weapons of mass destruction. The journal Nature also has a similar bird flu paper waiting in the wings for the same reason. And now both papers are currently under review by the US's National Science Advisory Board for Biosecurity. So how should sensitive, but nonetheless very important scientific results like this actually get handled? To find out more, I spoke with Mark Peploe. He's the news editor at Nature, which this week asked authorities around the world this very same question.
OK, so this all revolves around some research which has been done on the avian flu virus, H5N1. 2 groups of researchers have basically made a mutant form of this virus which is more easily transmissible between mammals. Actually, they've tested it in the lab, and it's ferrets that they use, and it's more easily transmitted just by ferrets breathing the same air. And that raises concerns that these viruses, if they escaped, could also be transmitted between humans and potentially trigger a huge pandemic.
There are 2 aspects to this, aren't there? One is, should we be releasing the information as to how to make these very pathogenic viruses that transmit very efficiently? Because there's a question over whether this is safe from a bioterrorism perspective. The other is the public health perspective. In order for scientists to be able to work out how to mitigate this threat, they've got to know what the threat is.
Yeah, that's right. And it's something that sometimes gets lost in some of the news reporting around this, in that these mutant strains weren't born out of some reckless desire by mad scientists to push the boundaries of high-risk science. So the issue is, like you said, should this work be published? An awful lot of scientists say yes, it absolutely should be published in full, because it's important to understand how deadly these viruses are and potentially develop treatments against them. On the other side, there are some people within the security community, but even scientists as well, that argue that the benefits that you gain from this sort of work are just not great enough to counter the risk of an accidental release, or the possibility that a terrorist could get hold of the recipe, if you like, and cook up some of this virus for themselves. Those in the security community take a broader issue, which is that some of the mechanisms for oversight of this sort of work really aren't sufficiently well developed. They're saying, look, the argument about this is coming up when this work has already been done. It's about to be published, and the security community is saying, well, look, we need a much more stringent oversight system to make sure that these conversations start happening before the experiments go on and not after them.
And where does a journal like Nature stand on this? You've got some information that you want to publish, which is for the good of the scientific community but may have political consequences. At what point does it become a problem with someone saying you can't put that out?
Well, because I'm the news editor of Nature, I can't actually speak on behalf of the section of Nature which publishes scientific manuscripts. But I know what our editor-in-chief, Phil Campbell's, position is on this, and that is that they acknowledge the concerns about this work. And at the moment, there is no decision about whether to publish the papers or whether to publish a censored form of the papers. What we're waiting for is for the US government to provide details of, if the papers are censored, how it would allow genuine researchers to obtain that detail that would inform their own work. And as long as there is a safe but efficient system for getting that information, that scientific information, to legitimate researchers who need it, then both Nature and Science have said in statements that they would be happy to publish the papers in a redacted form. So you basically outline what the researchers have done, but you don't give any of the recipes in public for how they did it.
Mark Peplow. But what is the work at the centre of this scientific storm? Ron Fouché, the author of one of those papers.
We've been working on H5N1 viruses that are circulating currently in Indonesia and causing massive outbreaks. And we've been studying transmissibility of this virus to humans and between humans.
Many people say H5N1 isn't a big worry because if it was going to jump into us, it would have done already. How do you respond to that?
Well, it is a big worry even when it jumps into us now because it kills people. It killed more than 400 people already. And of course, so far they've been isolated cases. But the fear is that the virus will adapt. It will change genetically such that it will become transmissible. And every case of infection of a human is a chance of the virus adapting to the human situation.
So when a virus does jump out of one host species, like a bird, in the case of H5N1, to get into humans, what does it actually take for it to grow efficiently in a human, a different host, and then spread from one host to the next?
We know pretty much what it takes to infect the first human. We know very little about what it then takes to be transmissible between humans. They have to adapt to attach to other cells than they're used to attach to. These cells express receptors, and they have to adapt to new receptors. And they also have to adapt to produce enough virus such that the virus can spread. And it does so by making genetic changes in the polymerase complex, and the polymerase complex is responsible for multiplication of the virus. But really, we don't know anything about what it takes to then become transmissible.
Many of the cases of H5N1 we've seen tend to stop with the person that gets infected. So they get it from a bird, but then they don't pass it on. So how can they die of it yet not pass it on?
So many of the human cases of infection, they contract the virus in odd ways, by drinking raw duck blood, for instance, or by getting the snot out of the beak of a fighting cock. And so they get huge amounts of virus in, and they get it generally deep down the respiratory tract. And deep down the respiratory tract, the virus can replicate quite efficiently. These individuals develop pneumonia, and they die as a consequence of that. The virus is not particularly well adapted to replicate in the upper respiratory tract. And we have always said that as soon as the virus gains the ability to replicate in the upper respiratory tract of humans, then we might be in trouble.
So how are you trying to work out what it's going to take?
We borrowed evidence from previous pandemics when also avian viruses changed and then caused infections in humans. And some of the changes that occurred in those pandemic viruses, we have introduced by genetic manipulation into an H5N1 virus. And that H5N1 virus now replicates in the upper respiratory tract of mammals. Now that virus has many of the hallmarks of a pandemic virus, but we found initially that it still was not transmitted. It was very surprising. And so what we did then is to put it into a mammal, let the virus adapt to the mammal for a few rounds, and then take that virus, and then that virus will become transmissible. And so by intelligent experiments, we were able to introduce 3 mutations into the virus. And then, because we didn't know the rest of it, we let the mammals do the rest of the story. And they accumulated 2 or 3 additional mutations are enough to make this virus transmissible.
Every time the virus goes into a new mammalian host, it has a new chance to adapt.
Yes, that's correct. So that's the message that we're sending out. Many of the mutations that we have introduced with genetic modification are already found in the field. So it's now a matter of chance of a mammal running into a chicken that has a virus with those mutations. And then in that mammal, it can accumulate the extra mutations, and then we would be in trouble.
You're saying that the mutations that you put into your experimental virus already exist out in nature if you know where to look for them?
Yes, so far there have been about 500 million birds infected, and we have sequenced the genome of about 1,000 of them. And in those 1,000 genomes, we already find the exact same mutations that we find in the transmissible virus.
But not all in the same virus?
Just not in the combination of 5 or 6 that we find in the transmissible virus.
Once you put those mutations or changes into H5N1, does it remain as pathogenic, as virulent as the wild type, or does it have to surrender some of that virulence in order to become fit to reproduce in humans instead of its more native bird?
Well, we had all hoped and also thought that this virus would be reduced in virulence, but the first quick and dirty experiments that we've done suggest that the virus is just as hot as the wild-type virus, and it kills a ferret in 3 days. In humans, it kills 95% of the individuals that get infected.
What's the moral of the story?
To be honest, I think that many scientists have, well, not just scientists, but also the policymakers are relaxing a little bit too much on H5N1 at the moment. Many scientists believe that only H1, H2, and H3 viruses can cause pandemics rather than H5, and many scientists think that it has to involve pigs. Many scientists think that viruses need to shuffle their genes rather than just build in mutations. And this investigation really showed that we should not be so relaxed about how to deal with the H5N1 virus, and I think the policy should be to start stamping out H5N1.
Ron Fouchier from the Erasmus Medical Centre in the Netherlands. He was speaking with me at the ESWI Influenza Conference held in Malta last September. So how do you think situations like this should be handled? We'd really like to hear your views on what we should do when people do invent deadly viruses like that could help to save mankind but equally destroy it. Do get in touch, tweet at Naked Scientists, or send us an email to chris@thenakedscientist.com. Helen.
Yeah, well, important and sobering stuff. Well, also this week, scientists have discovered the deepest and possibly the hottest undersea volcanic vents ever found, and they're encrusted in extraordinary deep-sea life. The Cayman Trough gouges a gigantic trench in the sea floor, 5 kilometres beneath the waves in the Caribbean Sea. And it's there that a team of researchers led by Douglas Connolly and John Copley from the National Oceanography Centre in Southampton detected a vast plume of scorching, mineral-laden water reaching a kilometre up into the water column. Here's geochemist Douglas Connolly.
Cayman Trough was identified quite a while ago as one of those interesting sort of missing pieces of the global ridge systems. It's isolated, sits on its own, and it's also one of the deepest places and one of the slowest spreading. It had been postulated that there wouldn't be any venting activity there at all. Basically, activity is dependent upon the spreading rate, is one of the old models that was out there. In the deep site, we've got extremely high pressure and perhaps the existence of supercritical fluids.
These supercritical fluids behave very strangely under the laws of physics. They're lighter than water but denser than vapour. And the team think that these extremely deep vents, which they've called the Beebe vent field after the first scientist to explore the deep ocean, could be one of the only places on the planet to study these fluids in a natural setting, including their effect on the way minerals are leached out of rocks. Connolly and his colleagues found unusually high concentrations of copper in the fluids rising up from the vent, which indicates the presence of these supercritical fluids. And along with the height of the vent plume, 4 times higher than that of other deep-sea vents, suggests the water could be as hot as 450 degrees Celsius. And despite the enormous pressure, life down there is thriving, as the team discovered by sending down a robotic submarine to take a look. Here's marine biologist John Copley.
Well, for biologists, we've wanted to go and explore the Cayman Trough for deep-sea vents for nearly a decade, because we thought it might be a key missing piece in a global jigsaw puzzle. What was a surprise was actually, yes, we see new species of shrimp down there. There may be a new species of anemone at the deepest site in their hundreds around these sort of cracks that seep warm water from the seafloor. But these are very similar to animals that we know, but from a long way away, 2,500 miles away in the Atlantic. And it suggests there's a lot more traffic. Animals are getting around in the deep ocean, perhaps a lot more than we thought before.
Another world first came from this study, and that was the unexpected discovery of a hot vent in a much shallower site on the upper slopes of an undersea mountain called Mount Dent. This sticks 3 kilometres above the Cayman Trough, although its peak is still 2 kilometres beneath the waves. The Mount Dent vent was also found to be swarming in life, and since submerged mountains like this are quite common, it hints that deep-sea vents could be a lot more widespread than previously thought, and they could offer stepping stones for vent animals to disperse between vent fields.
Naked Oceans podcaster Helen Scales. And that work was published this week in Nature Communications. And you can hear Helen's full interview with the lead authors, John Copley and Douglas Connolly, on our Special Editions podcast. That's at nakedscientists.com/specials. Or look up the Naked Scientists Specials podcasts on iTunes. Now, with more top stories from the week in science, here's Meera Senthilingam with our Naked Scientists news flash. Kicking off with some potentially bad news for any smokers out there who recently made resolutions to quit.
Nicotine replacement therapies have been shown to have no long-term benefits for smokers trying to kick the habit. Following 787 adult smokers over 5 years, Gregory Connolly and colleagues from the Harvard School of Public Health found 1/3 of smokers relapsed when trying to quit, and saw no difference in this relapse between those using therapies such as nicotine gums and patches to those using other methods or going cold turkey in the long term.
There's multiple factors for relapse. There's social cues, there's cigarette-driven cues, and there's probably a diminishing over time of the personal will to quit. In the past, studies have looked at laboratory trials and then taken those findings and put them in the real world. What we found, when you put it in the real world and you look at the long term, they're just not having an effect. So what we have to do is combine our laboratory trials with trials in the real world, combine them, learn, develop better mechanisms, and then make this planet smoke-free.
Our galaxy has as many planets as it does stars, according to scientists at the University of St Andrews. Using gravitational microlensing to find planets located further away from their stars, Martin Dominic and colleagues discovered a large population of planets within the Milky Way, which calculations have been estimated to equal the total number of stars in the galaxy, and further showed that stars without associated planets could be the exception.
In the Milky Way alone, we think there are 100 billion to 300 billion stars in there. Now we took a small sample. We find that the number of planets is actually comparable to the number of stars, or even larger. So that means just in the Milky Way alone, there could be 100 billion planets. Interestingly, we find that the abundance of the smaller planets is much larger than the number of gas giant planets like Jupiter or Saturn. And that is quite interesting if you think about places where you want to look for life.
Fungi could hold the key to fighting lead pollution, states research published in the journal Current Biology. A known environmental pollutant, lead is a widely used structural and industrial material worldwide, with previous efforts to contain or control levels in contaminated sites proving challenging. Now, Geoffrey Gadd from the University of Dundee has found that fungi can be used to transform lead into pyromorphite, its most stable mineral form.
We've made quite a remarkable discovery in that certain fungi can attack the metallic lead, which will result in a completely new mineral form, pyromorphite, which is a kind of lead phosphate. And in fact, it's the most stable lead mineral that exists in the Earth's crust. So we've shown that really activities of living organisms can do this, which gives the intriguing possibility that perhaps somehow you could encourage the organisms to do this or act themselves in polluted sites.
And finally, a carnivorous plant residing in the tropical savannas of the Brazilian Cerrado region uses sticky underground leaves to trap and digest nematodes. Caio Pereira from the State University of Campinas fed nematodes labelled with isotopes of nitrogen to the plant Philcoxia minensis, and found significant levels of nitrogen thereafter in the leaves of the plant, proving the plant's digestion and absorption of the worms. It's thought the plant uses phosphatase enzymes to directly break down the nematodes for nutrition.
This plant is producing enzymes and digesting the nematodes that get trapped within the sticky leaves. And this suggests that there is more transspecious ways and more strategies that the plants are using to secure nutrients, especially in severely stressed habitats.
And the work was published this week in the journal PNAS.
That was Mira St-Fillingham. And all of those stories and everything we've been discussing on this week's show can be found, along with their references, on our website. That's thenakedscientist.com/news.
Distilling the best science. The Naked Scientists.
And this is The Naked Scientist with Chris Smith and with Helen Scales. The Earth is under constant bombardment by particles spewed out by the Sun. They're responsible for the spectacular aurorae, the so-called northern and southern lights. But solar storms can also disrupt satellites, communications and power supplies, and so scientists have now produced the first ever map that shows which regions of the UK power grid are at the most risk. Dr. Kieran Beggan from the British Geological Survey in Edinburgh spoke to Planet Earth's Sue Nelson about the map and the damage that can be done to power grids.
Aurora coincide with large-scale changes in the magnetic field, and magnetic field changes can induce electrical currents into the ground. These are normally very small, but when you get very large aurora, then the electric fields can be larger. And the electric fields or currents tend to flow through the rocks in the ground, but if they become large enough, they can then flow through into the power system through the transformers which are connected into the ground.
Approximately how many of these power station transformers are there around the UK?
There's approximately 600 at the moment, and they stretch all the way from the very north of Scotland all the way down to the south coast of England.
There have been occasions around the world, famously one in Quebec, where these produce more than just a brief power outage, don't they?
Yes, so the very famous incident occurred in Quebec in 1989, where a very large geomagnetic storm, the largest one in that decade, caused a transformer to trip in Quebec, and then there was a chain reaction event all the way down the east coast of the US. And a similar incident occurred in Sweden in 2003, and that was, again, a geomagnetic storm triggered a collapse in a transformer, which then caused all the electricity in the country to fail.
So how likely is that to happen in the UK? Is it a real possibility?
It's very hard to say how likely it is. At the moment, we're just trying to identify where it might occur, and that's what our map has tried to do. So our map is basically a very simple representation of the UK power grid. And what we do is use the geology of the UK, because that is the controlling factor actually, to try and figure out how the electricity flows between one part of the UK and another when there's a very large geomagnetic storm. So we've discovered that the extremities of the grid are the bits that are most likely to be affected by geomagnetic storms.
And by extremities you mean, say, maybe Cornwall, for instance?
Yes, so the north part of Scotland is where the electricity tends to flow into the grid, and then it'll tend to flow out at the other extremities, such as in Wales, in Norwich and in Cornwall.
Does that mean that the type of rocks in those particular areas, like Cornwall, like East Anglia, are the same? What type of rock are we talking about?
Rocks have different electrical properties. So if you have a hard rock, like a metamorphic rock or a granite, for example, it tends not to conduct electricity very well. So the electrical current will tend to flow along the surface. It's much more likely to then flow into the power grid. Something like chalk or sandstone, which tend to be what the south of England is made from, is actually more porous. It tends to have a little bit more water in it, and so the electricity will tend to flow deeper into the ground, and that way it will sort of avoid flowing into the national grid.
So you now know then which parts of the UK are most at risk, because this map that you've produced never been done before. What can the power companies do about it?
One thing that they're going to do is install monitoring equipment at certain regions that are more likely to be affected. And over the years, they do know that geomagnetic storms cause problems, but they've never been able to understand quite where the problems are. So this map will help them identify which regions they should be installing equipment in, and also which transformers they should be monitoring more closely for signs of damage, for example.
Now, the Sun famously has its sort of 11-year solar cycle. I assume this affects the possibility and the number of geomagnetic storms that you get during these 11 years as well. So what part of the cycle are we currently in?
So we've just come out of a very deep sort of low part of the cycle, and we're moving through the sort of middle part of the cycle, and it will peak in 2013, around about mid-2013, and then it tends to fall off again.
So this, in fact, is perfect timing then. You've produced the map with 2 years' notice, effectively, for the power stations to act on your information and your advice.
Yeah, that's correct. This has been driven from government level, actually. There's been a lot of concern in the last couple of years that natural hazards to the UK have maybe not been studied as much as they could have been. So this is all part of just looking at what natural hazards there are threatening the UK at the moment, and as solar or geomagnetic storms are one of them, we're looking at ways to try and understand and alleviate those effects.
Dr. Kieran Beggan from the British Geological Survey, BGS, talking to Planet Earth podcast presenter Sue Nelson. And if you want to hear more news from the natural world, then you can find a link to the Planet Earth podcast on our website, nakedscientist.com, or via the Planet Earth online website. Look them up on Google. And returning now to our theme this week on cybernetics, cyborgs, implants and prosthetics, scientists are moving closer to developing ways to interface with the brain and to decode what nerve cells are saying to each other. Professor Andrew Schwartz is working on this at the University of Pittsburgh and is with us now. Hello, Andrew.
Hello.
What sort of signals are you trying to eavesdrop on?
Well, we record from a part of the brain called the motor cortex, and this part of the brain is thought to have a lot to do with controlling movements. We're particularly interested in arm and hand movements. So the neurons we record from seem to be related to aspects of moving the hand and arm, and particularly the direction and speed in which the hand moves.
In other words, if you were to look at the surface of the brain and specifically the bit of the brain that we know relates to movements, there's a map of the person or the body on the surface of the brain, and different bits of that map relate to different body parts.
That's right, in sort of a coarse way. That's a general way of looking at it.
So when you are recording from different clusters of nerve cells, what does it sound like? What sorts of conversations do nerve cells have?
So we can record from individual nerve cells, and the sort of message that they send is the rate at which they fire action potentials. So action potentials are these little impulses of electricity, and the time between those impulses carries the information. And so what we found is that when you move your arm in different directions, that each neuron has a direction in which it likes to fire fastest in. And we can take account of that to try to decode the way that you intend to move your hand. And so over the years, we've built up a rather elaborate decoding mechanism where we can look at the direction and speed of the arm in three-dimensional space, and more recently, the angle of the wrist, and now the shape of the hand and fingers. So we can get a pretty much a complete representation of what you're trying to do with your hand by tapping into these signals.
So rather than just turning individual muscles on and off, these motor cells in the motor part of the brain are active when they want to make a part of the body move to a certain position in three-dimensional space. So, in other words, if you wanted to hold your hand out at sort of the 2 o'clock direction at 45 degrees to yourself, there would be a bunch of cells that would fire the most when you were going to do that.
Right, and the interesting thing is it's not just the cells that like to fire in that direction, but other cells will actually stop firing when you move against their preferred direction. So what we do is we look at the entire population because all the neurons carry some information about that movement. So one of the critical things about all this is that we look at the large population of cells, not just at a few individual neurons.
It's quite clever. So you're looking at things going off as well as things turning on. How many nerve cells do you record from? If you want to decode meaningfully what the brain wants to do, how many electrodes do you need?
Well, we've used as few as, say, 30 neurons to get a good representation of X, Y, and Z movement, or three-dimensional movement in space. But typically what we do now is record from 100 to 200 neurons, and we get a more elaborate decoding. So now we can record or decode other aspects of movement as well.
So what's the sort of next step then? So at the moment you can read those signals off, but translating that neurological chatter into something you want a computer to do or a robot to do, that's a whole different ballgame, isn't it?
Well, yes. Actually, the decoding principle we've known about more or less for 20 or 30 years. just from doing basic research. When we study monkeys, and when monkeys move their own arms, we can record this activity and then correlate the activity to the monkey's own arm movement. Now, in the last 10 or 15 years, what we've done is taken that signal, and instead of using or correlating that to the monkey's own movements, we use that to drive a robot arm, and the monkey can actually see that robot arm and control that robot arm without moving its own arm. So we've sort of taken and tapped this intention out and given it a behavioral meaning to the animal now.
And I suppose one of the things which Kevin was saying at the beginning is the brain is extremely plastic. So even if you are not recording from precisely the right cluster of cells to do exactly what you might want to do or want to achieve, with training, the individual, be it a person in the future or a monkey today, could still nonetheless learn to think along the right lines. The brain would maybe rewire itself very slightly in order to achieve the desired movement using the electrodes you've plumbed in.
Actually, yes, that's one of the fascinating things. I would word it slightly differently. I'd say that we have to have a model of how this activity works or what it's being used for, and our model is inaccurate. And, as you said, we're only recording from a few of the billions of neurons that fire during every movement. And so our decode is rather inaccurate. But what the animal is able to do is to learn the algorithm that we're using to decode this and actually help us by making his neurons fire more in line with our model. So essentially, what the animal is doing is learning our model and helping us in that regard.
And one can obviously see that if you can decode what the brain wants to do in people or individuals who have some kind of injury or an interruption of the flow of information from the brain to the motor centres in the spinal cord that would enable them to move, you could then reconstruct movements for them or enable them to control and interact with their environment better. What about going the other way, though? What about putting information back into the brain? Would the same techniques you've developed to listen to neurons also enable you to talk to them?
Well, that's an open area of research, but that's exactly what we're trying to do. We're in process along with several other laboratories. What that would involve, in our particular case, is putting sensors on the robot's fingers and joints so that we can impart tactile information and joint information back to the subject. And the way we hope to do that is by stimulating with electrical pulses, again, in the sensory regions of the brain to try to impart this information back to the subject.
Thank you. Andy, we're going to invite Marcus and Kevin to come back in and join us because we have all of you with us. We're talking this week about cybernetics. It's Helen Scales and Chris Smith, and implants and things that we can add to the body to make us part man, part human, part animal, part machine, whatever it is. And if you have any thoughts or comments on that, email chris@thenakedscientist.com. We've got a huge number of comments come in on Facebook. I actually asked people earlier, what do you think about the whole idea of actually going that extra mile where we turn ourselves into a part machine, part human? And quite a few people made some interesting comments. Evan Gertz got in touch and said, no problem, we've already been living in lab-modified environments for years. Fake food, fake medicine, fake houses, not to mention they were all made with machines. I think it's great. I would like some wings, though, he points out. We also got one from Nish Nair who says, I support such advancements, but I think the inventions such as those mentioned are going to take a very long time. When humans do manage to create a physical interface between electronics and the biological brain, the real revolution will start before we know it, and we'll be plugging in chips and learning concepts in seconds like you see on The Matrix. And we also got one from Michelle and Nakagawa who says, we're all connected to the net with our phones and computers and other devices at all times nowadays. This has impacted on the way we interact with our social environment. So I don't consider a chip inserted into us that can connect to the WWW such a great leap. So, Kevin, I guess this must be music to your ears.
Oh, yeah. I mean, it's great. It's all positive. It's interesting. I mean, Michelle pointing out we are already very much connected. This is looking at the next step. At the moment, we're still communicating via motor sensory input-output. Well, we can go that bit further. As Andy's been talking about, signals directly from the brain, signals directly into the brain. So the whole basis of communicating just with your brain, that's going to be the future.
Helen.
Well, Josh Barry got in touch with a great question that I really want to know the answer to, which is, could we surgically add a hard drive to our brain to basically increase our overall memory storage? Because I think I could do with one of those. Are we anywhere near being able to, I suppose, download our memories and add to that? Kevin, any thoughts on that?
You can stimulate memories. That's about as far as we've got. So applying signals at particular parts of the brain, someone says, I can remember when I was a young kid and so on. But actually finding where they are, recording them, some people feel memories are quite spread around in the brain. So I don't know we yet fully understand what memories are. But I share the excitement, the possibilities. In long term, one would hope we will be able to do it, but I think it's a long, long way away, yeah.
Andrew, what about the electrode side of this? Because this is more where you're working, literally the brain-machine interface, quite literally. What about the concept of actually getting information in and out like that with a sort of external hard drive?
Well, again, as Kevin said, we know very little about how memory really works in the brain. There is actually a group that's trying to make, for instance, an artificial hippocampus, but I think at this point it's a lot more engineering than it is science. So, again, as Kevin said, there's hope for the future, but right now I think we're quite a distance from that.
While you're there, Andrew, we've also heard from Anita, who's in Leigh-on-Sea. She said her daughter suffers from reflex sympathetic dystrophy or complex regional pain syndrome. She's actually asking specifics about treatment for that disorder, but if we consider pain more generally, one of the things Kevin mentioned earlier was putting deep brain stimulators in to control things like mood. I guess pain is also a possible target, isn't it?
Well, there's been a lot of good research on pain lately, and there are a number of, I would say, what we call neuromodulatory devices out there to try to stimulate in different parts of the nervous system, both in the brain and the spinal cord, to try to alleviate some of these symptoms.
Andrew, thank you. I've also got a comment here from Seth Robbins on Facebook, and he says, we've been enhancing our abilities beyond our natural capacities through tool use since we first picked up rocks, and merging our tools has always been the logical next step. This isn't going too far, it's simply evolution. I guess that goes along with what you're saying, Kevin. It's just another way of fitting into the modern world.
Yeah, and I think it's really the next step. It's linking more directly with the brain, because even with using tools now, whether we're moving things or whether we're taking signals in through our ears and so on, it's the old way of doing it. There's an interface, and if we can short-circuit the interface and put signals directly into the brain or take signals from the brain, it's the next step. It's an evolutionary step, how humans are now technologically speeding up evolution.
Marcus, what do people think about this? When you say to them, we're going to put a chip into your eye, how do people feel? Do they regard themselves as a bit weird because they're a cyborg, effectively?
Not at all. So far I'm seeing patients in the eye clinic who are interested in the technology because they are blind, and it gives them the possibility to maybe see things again. So they're highly excited to be part of research and be part of the project. But I would not think that they would consider themselves a cyborg or weird in any ways. It's just a different form of camera technology which is connected directly to the eye rather than through the retina indirectly.
And this isn't something you've come across, Kevin, with people feeling a bit strange because they are literally now part man, part machine.
No, I think one thing that's interesting is that with an implant, whatever, even if it's an artificial hip, that sort of implant, very quickly you regard it as being part of you. It's not like wearing a pair of glasses and you put them down. So when you've got an implant, quickly it's you. It's technologically different. So I would guess the people with the retinal implants, they wouldn't think, this is an implant. Very quickly they think, it is me. I can do those things now, which is tremendously exciting how mentally you take these things on board just as much as physically.
And Kevin, you have had a couple of implants yourself, and is the reason that you volunteered because you couldn't find anyone else to do it, or because you wanted to do it yourself?
No, I actually get quite a few volunteers, even now, and I actually have 3 of my undergraduate students who have implants, not the same type, not the neural type, but to be honest, for me, it was quite dangerous what we were doing, particularly the Utah array, the 100 electrodes fired into my nervous system, so there were dangers associated with that, but I also wanted to experience for myself what it felt like.
We've got another question along those lines of experiencing the world in a different way. Andrew Reitemeyer got in touch. He wanted to know what the chances of us developing the ability to sense other fields like magnetic fields. Has anyone done anything on that? Literally kind of tapping into the Earth's magnetic fields around us and allowing us to navigate and see our way around in a different way. Is anyone doing anything like that?
It's a very, very good point. Very exciting. I mean, I have students at the moment, 3 students. We have ethical approval. They actually have magnets implanted in their fingers, and they can feel. I mean, literally, if they go into a bank, they can feel the EM signals. What we're using it for, they have the magnet in the finger, a little coil of wire around the magnet, and then that is attached to different sensory input. So these are students doing their course. They can feel ultrasonic signals, like feel distance or feel infrared, which can be a heat signal. So it's converting different signals to magnetic signals. We haven't actually tested whether they can follow their finger and know which way to go as a compass would. That's an interesting one. We'll have to try that.
Presumably you'd have to be able to pick up very, very small magnetic fields. I mean, it's like a compass, I suppose. It's a human compass. That'd be fantastic.
Yeah,
never get lost.
We try. Well, I don't know about that. So it is exciting trying things like that, though.
And just in 30 seconds, Marcus, Gerald McMullen wonders whether you could provide him with a macro-focusing lens so he can read the small print without having to buy arm extensions.
I think to go with reading glasses is probably the much easier way than trying to do any complicated implants on that case.
Even if it does involve a forearm extension. Marcus, thank you very much. Helen.
Well, now it's time to go over to Hannah Critchlow for our question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
With New Year's resolutions in full swing, here's a sweet thermal caramel quandary for us to sink our teeth into.
This is Jeff from Encinitas, California. I made several batches of caramels over the holidays using a recipe that combines corn syrup, brown sugar, condensed sweetened milk, and butter in a saucepan. This year I was using a new digital thermometer and was surprised to observe that rather than rising at a constant rate throughout the entire cooking time, the temperature would rise steadily for a few minutes, then remain constant for several minutes, and then start rising again, repeating this several times through each batch of caramels. Why would the temperature rise so inconsistently?
So why should sticky stuff in the pan get hotter in stages? With the answer, here's Cambridge University PhD student Amy Chesterton, who specialises in the chemistry of cooking.
When you add heat energy to a simple substance, it leads to an increase in the kinetic energy of the molecules, so the temperature increases. If we drew a graph of this, the temperature would increase along a straight line as we added more heat energy. Sugar syrup isn't simple though, because there are chemical bonds between the atoms that form the molecules and even between the different molecules. These hold the water molecules and sugar molecules together, preventing them from evaporating when the mixture is cool. When the mixture is heated beyond a certain temperature, it begins to boil. This causes the molecules of water to break apart from one another, allowing the water to escape as steam. This uses up energy, so the temperature increases more slowly while this is happening. At other temperatures, sugar molecules themselves begin to break apart, which also consumes energy, again slowing the increase in temperature when this happens. And at other temperatures, the sugar molecules begin to bond together to form long chains, which is what is happening when you actually make caramel. Forming new bonds like this releases energy, which causes the temperature of the mixture to increase more quickly. This is why it's hard to only slightly caramelize sugar without burning it. So returning to the graph analogy from earlier, if you plot a graph of temperature against time for heating sugar syrup, there would be flatter areas where bonds are breaking and steeper ones where they are being formed.
So, the inconsistent rise in temperature that Jeff observed whilst cooking his caramels was due to bonds between water molecules and inside sugar molecules being broken, and new bonds being made as the caramel cooked. This caramel cooking conundrum caused quite a stir amongst all of you. According to retired science teacher John Wynnham from Sussex,
in the case of the caramel, the solid sugar will reach its melting point. Now, when a solid melts, the forces of attraction that hold the particles of the solid together in a lump start to loosen and break. And it's this process that absorbs the energy supplied instead of it being used to make the particles move faster. And consequently, the substance will stay at about the same temperature until melting is completed. Hence, the temperature of the mixture will not constantly rise.
And by email, Phil Sands from Portsoy, Scotland, as well as Blind Pete, who wrote on our forum, both correctly speculating that this effect was down to phase changes, similar to when ice melts to make water. So, with that quandary sorted, next week we'll be getting our heads around a question from Gerard Dunn.
I've always been told that there are no pain receptors in your brain, so what I would like to know is why does it feel like the pain is inside my head when I have a headache?
So what's going on in your head during a headache? Send your thoughts to chris@nakedscientist.com, tweet @nakedscientists, write on our Facebook page, or join in the debate on our forum, which is at nakedscientist.com/forum.
Thank you very much, Hannah Critchlow. And as Hannah says, you can get in touch, chris@thenakedscientist.com, if you have an answer to that one. Well, that's all we have time for this week. Thank you to our guests, Andrew Schwartz from the University of Pittsburgh, also Marcus Groppi from Oxford University, and Kevin Warwick from the University of Reading. Next week, we're turning into sun worshippers because we're going to be looking at the subject of vitamin D, which is created in the skin in response to sunlight. But we'll find out just how vitamin D deficient us lot who live up here in the pale, pasty, frozen north actually are. Thank you to our production team, Tom Simpkins, Miracent Thalingam, Ben Vousler and Hannah Critchlow. Thank you to Helen Scales for helping to co-present this week. And do join us next week for more science. chris@thenakedscientist.com if you have any questions.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.